Hello everybody, welcome to my video. I am Alp Kızılos, a senior student at 9 Eylül University, Department of Electrical and Electronics Engineering. Today I'm gonna show you how to create a simulation environment for a 4 degrees of freedom robotic manipulator. To create a 3D simulation environment, I use Peter Corke's Robotics Toolbox. Firstly, I created a graphical user interface by using this toolbox to obtain the angle values of the motors and desired positions from the user. In this project, it's aimed to observe the motion and trajectory path of the robotic manipulator in this portion of the screen in 3D simulation environment. The user can enter motors angles here and click the forward button. When user click the forward button, a forward kinematic function is applied to robotic manipulator and the resultant position of the robot calculated. The coordinates of the resultant position showed here, x, y, and z, and the motion of the robot and trajectory path of the robot can be observable at this portion of the screen. Also, the user can enter the desired x, y, z position of the robot and click the inverse button. This time, an inverse kinematic function applied to robot manipulator and the desired theta angles to reach this position that's entered from the user are calculated by using an inverse kinematic function, and the resultant theta angles are shown here. Also, the motion of the robot and trajectory path of the robot can be observable at this portion of the screen. Before getting detail to GUI, I want to talk about the specification of the robotic manipulator that used in this project. The illustration of the robotic manipulator is given here. Our robotic manipulator has 4 degrees of freedom, but has 6 joints with 2 fixed joints. One is here and second is here. All joints have local reference frames. That's shown: base revolute joint local reference frame, the first revolute joint local reference frame. And using these illustrations, the edge parameters of the robotic manipulator can be obtained. The edge parameters are necessary because in 3D simulation environment, the edge parameters are used to create the 3D rigid model of the robotic manipulator. So, theta parameter is represent the turn in z-axis. D parameter represent the joint offset, and A parameter represent the length of link, and alpha parameter represents the joint twist angle. Let's look at the first 0 and first link. Here, between theta 1 angle is the turning motor angle of the length of the base revolute joint, and this revolute joint can turn around its z-axis about theta 1 degree. Z-axis of the base revolute joint is in this direction. Z1 axis of the first revolute joint is the out of the page. So there is a joint offset with which is 2.2 cm between base and first revolute joints here. Length of the link is 0 and twist angle is 90 degree because here Z0 axis in this direction and Z1 axis 90 degree apart from Z0 axis. So let's look at the first and second joints. Theta 2 angle is the turning angle of the first revolute joint, and the parameter is 0 because Z1 axis of the first revolute joint is the out of the page. Also Z2 axis is the out of the page. So there is a length of link is 13 centimeter here, and alpha parameter is 0. Just like that, whole DH parameter table can be filled. It is important to note that each revolute joint has a motor to turn around its z-axis, and in reality these motors cannot turn around 360 degrees. Because of this reason, each motor has a limitations, and these limitations is important because in the simulation environment if we want to get a correct simulation, consider these limitations, which is given here. The motor angle limitations is given in this table. For example, limitations of base revolute joint is between -100 degree to 100 degree. Now let's look at how we can create a graphical user interface using Matlab. Type the guide at the command window and click the blank graphical user interface, and you can name the figure. Let's name as robot and click OK. Then automatically the code of this graphical user interface is come here. We can add some text box to graphical user interface here, or we can add some here push button to graphical user interface, and also we can add some access to this GUI. The text is used for a box that user enter the necessary parameter here. Let's double click on this, and we can change the parameter of this edit text box. Maybe we can change the string, or let's empty, and we can change the tag of the box. Let's call it as theta angle, and here the user can enter some numerical values in these text box, and the obtained value called as theta, which is theta angle of the motor. And here's a push button. We can change also parameters of this box. Again, double click on box and change the string. Maybe let's call it as forward. And we can change also tag of this button. Let's call that forward again. And this box create a function in the main function of the graphical user interface. To go the function block, view callbacks and click callback. Here is the function of the forward push button. When the user click the forward, this function is executed, and we can write the necessary code that we want to do when they click the forward button in here. Also, this axis is used for the simulation. In our project, this axis shown for the motion of the 3D robotic manipulator. Okay, let's examine the graphical user interface that I created already. Here, a user can enter some theta values, which are the angles of the motor, this text box, and when click the forward button, using forward kinematic function, the resultant position of the robot is calculated and printed here. And motion and trajectory path of the robot can be observable in this axis screen. Let's examine the forward kinematic function block of this graphical user interface. Here, obtained theta values are converted to radian per second quantities. Then, the h parameters of the robot are defined, and length of the link of the robotic manipulator are also defined. And using these DH parameters and link lengths, each link of the robotic manipulator are defined here. And using serial link commands, each links are connected to each other and create a robot. After that, initial theta values are defined as 0. Then let's assume that theta 1 angle is 20 degrees, and between 0 to 20 degrees separated in 20 equal parts. This is due to obtain a motion in the 3D simulation environment. How we obtain the motion? This by printing each divided parts on the simulation screen, the robot obtained as it can move around a path. And also trajectory path of the robot should be drawn, and to draw the trajectory path of the robot, these divided angles are sent a function, forward kinematic function, that written by Ufuk Çamdır with the h parameters of the robot. And these functions send us a x, y, and z coordinates of the robot for each divided theta parts. And by plotting these position on the same screen by plot3 command, we can draw the trajectory path of the robot. And using robot plot commands and divided theta angles, we can do the simulation of in 3D environment of the robotic manipulator. And finally, using a forward kinematic function again and theta values, we can get the resultant position of the robot, and using these commands send the resultant position to graphical user interface screen. Okay, then let's examine the inverse kinematic operation of the robotic manipulator. When user enters the x, y, and z positions of the robot, these positions are the desired position of the robot, resultant position of the robot, and click the inverse button. The code of this function block returns us for theta values, which are the angle of motors of each revolute joints. And this angle allows us to reach the desired position of the robot. And again, similar to forward kinematic, the motion and trajectory path of the robot can be observable in this axis of the screen. Let's examine the code. When the inverse button is pressed, the position values are taken using these codes, And remember that our robotic manipulator's motors has some limitations, and these limitations are defined in here. This part of the code is related with the forward and inverse kinematic function of the used in the code, so it is not related with the specification of our robotic manipulator. And like previous case, similar to previous case, link length of the robot manipulator is defined, the edge parameter of the robot manipulator is defined, and each link is created as before, and using serial link commands, each link is connected together and create our robot. In this case, position, since we know the resultant position of the robot, to draw the trajectory path of our robot, we divide the position between 0 to resultant position some parts. For example, in this example, 10 parts. And each divided part is used to draw the trajectory path of our robot using again plot tree commands, like previous case. Here, the theta angle values is found by using inverse kinematic function, and this function needs the edge parameter of our robotic manipulator, and each of these divided position vectors and limitations of our robot, and obtaining the divided theta angles, we can simulate the 3D model of the robotic manipulator by using robot plot, and each moment we can plot the theta divided theta parts on the screen. And finally, using inverse kinematic function, again we can find the resultant theta values of each motor, and using this command the theta values is printed on the graphical user interface screen. Okay, finally let's do some examples. Firstly, we start the program here, and let's first try to forward kinematic solution for our robotic manipulator. Remember that our motors have some limitations, and while I am entering the theta angle values in these boxes, I will consider the limitations of the robot. If I do not consider the angle limitations, our simulation maybe draw the unwanted situation of the robot. Maybe links of the robot can collapse or something which cannot be possible in reality. So the angle limitations will be considered while entering the theta angles. And let's enter some theta angles. And finally, and we know that in backstage of the graphical user interface, since we separate the position range of the robot in many parts, many times forward kinematic function is called, and many times forward kinematic function is executed. And let's click the forward here. 20 times forward kinematic function executed in the backstage, and finally our robot has reached the desired point. And let's change some angle values. Let's change theta 2 as 25, which in the limitations again, between the limits again, and click forward button. Again, backstage function is here. And let's try some inverse kinematic operation. Here, since we again separate the theta angle values in many parts, and each of divided parts send the inverse kinematic function, even if one of the theta solution is not possible, there is an error message printed here, and our simulation would not work accurately. So actually we try to find the possible locations that robots can reach, and let's try something. Change the y value as -10, and let's change the z position 15 and click inverse. Again, here we can show the applying inverse kinematic, and robot has reached the desired point. Let's try to any different points. Let's change x this time. It's 5 maybe. Maybe we can change the z. That increase the value of z. Maybe 17. Click inverse button. This position is the initial position of the robot that defined in the code, and we can show the motion in the 3D simulation environment again. That is the end of the video. Thanks for watching.